So I think we can get started. Welcome everyone to this, by now, tradition to have a panel discussion centered at the Nobel Prize in Physics. And I will be very brief now. My name is Mats Larsson. I'm director at Albanova. And after this panel discussion, there will be a reception outside the Albanova restaurant and hosted by Albanova. So there will be some wine and cheese. And now I will hand the word over to the moderator of this panel discussion, which is Yegor Babayev from KTH. Yegor.
Welcome, everybody. It is a great pleasure for me to be here and discuss this year's Nobel Prize that recognizes the seminal work on the importance of topology in physics. In 1970s, before these developments, the dominant paradigm in condensed matter physics was due to Lev Landau, that we can classify different states of matter and transitions between them by symmetry. I will be brief, and as we will hear from the panel, that these works were some of the seminal works where there was a shift of paradigms that not only symmetry is important in physics, but also topology. And as any paradigm shift, it didn't occur overnight, and also it had lasting consequences. And in this panel discussion, we will try to look back at the events and contributions that led to this paradigm shift and future implications. So the panel consists of Emil Bergholz, assistant professor at Stockholm University, who is also a Wallenberg Fellow of the Royal Academy, Subir Sachdev, professor at Harvard University, Shivaji Sonhi, professor at Princeton, Frank Wilczek, who is now local Stockholm University professor, and Ashwin Vishwanath, Harvard University. And I'm now passing my microphone to Emil.
Thank you very much. It will be a pleasure to introduce these concepts that Igor mentioned briefly in terms of simple pictures to sort of let's see if I can actually get these simple pictures appearing. All right, so I'll tell you about this year's Nobel Prize that was awarded for theoretical discoveries of topological phase transitions and topological phases of matter. This sounds very complicated, but you can get some nice insights from studying very everyday pictures. So here we have pretzels and donuts and ordinary buns, and from a topological perspective, these are distinguished by the number of holes in them, and that's a global property in terms of which gives you integers. So in this way, the two donuts here on the right, they are topologically equivalent. Even though one is dipped in chocolate, both of them have one hole. The pretzel is different. This particular pretzel has 3 holes, while the ordinary bun here has no hole. All right. So 2 more concepts will be important, and that's symmetry, that's already mentioned, and fractionalization, that I'm sure you will hear more about from the other speakers. So standard phase transitions are described essentially by the Landau paradigm. So at high temperatures, as you can see here, you have disordered states. And that means that entropy wins. We have many, many configurations that are disordered, and therefore the free energy is minimized by random-like configurations like this. However, if you lower the temperature enough, you have a phase transition to an ordered state which has much less symmetry. It's in fact described by local order parameter. In this case, you can see that the arrows are all pointing in the same direction. So we have long-range order in this system. That means that if you know where the spin points up here, you also know where it points far away from this first spin. So what are topological phase transitions? Well, Kosterlitz and Fowles, and in fact independently Berezinski had some of the similar insights, pointed out that in certain two-dimensional systems, phase transition can be driven by topological objects, in particular vortices and anti-vortices. So what are those? Well, here's a vortex, and here's an anti-vortex. These are clearly global things, global objects. And that's one of the key ingredients for being topological, the other one being assigned an integer. So if you look at the vortex and follow a random, well, any path enclosing the center of the vortex, and you go clockwise around it, you will see that the spin winds one orbit. So the phase shift divided by 2 pi is 1. If you now look at the anti-vortex and go on a similar clockwise closed path, the spin winds the other way. That gives the opposite integer, -1. So what Kosterlitz, Fowles, and to some extent Berezinski realized was that you can have an entropy-driven transition without symmetry breaking or local order parameter, where you have pairs of these vortices and anti-vortices that are at low temperatures, they are confined, bound to each other. But at high enough temperatures, they deconfine and move as independent objects. Okay, that was the phase transition story. So to go to topological phases, we have our special first topological phase, that's the quantum Hall effect. And those are 2D electrons in a strong magnetic field. And what happened, what was extremely surprising at the time and in the early 80s, when von Klitzing did the experiments, is that if you look at the transverse resistance, it doesn't follow a linear slope, as it should do, classically. Instead, it has these quantized steps, and they come in an incredibly well-quantized way. They are exact up to 10 digits or so. And it can be expressed in very natural constants, h over e squared. So what's the explanation for this? Well, a very simplistic picture of this is that if you look at the lowest energy states, they have this sort of orbital motion about them. So if all the electrons wants to be confined in the lowest state, we get a picture like this. We fill up the entire plane by these lowest energy states. Now, the current cannot be transported through the bulk of this system. The states are just confined to making these orbits where they stand. So there is no current through the system. However, if we make an edge, we see that we get these skipping orbits. So the electrons are not allowed to make these circular motions, but instead scatter in sort of a skipping orbit manner. So on this edge, we get the current upwards, and on the opposite edge, we get the current downwards. And this is something very weird, right? We have only current flowing in one direction. But this looks a little bit like fine-tuning. What if we didn't have enough electrons to fill all of these states? Then we don't expect this picture, but on the other hand, we see plateaus here, and that means that we have a range of stability of these states. So Fowles and his collaborators stepped in and calculated actually for a quantum Hall system on a lattice, calculated the conductance, which is the inverse resistance in this case. And they found that the expression is actually topologically invariant. So you get out e squared over h times an integer. This integer is very much related to these pretzels and donuts again. And this is something that's very robust. So even if you do a little bit to the system, this conductance will stay exactly quantized. Some years later, Haldane came and said that actually you don't need a magnetic field to get this kind of effect. What you need is a broken time reversal symmetry. And what Haldane did is that he introduced a very simple toy model, which he himself has sketched on his whiteboard that's supposed to be in his living room, or some of his rooms. So one can see this as one instance of fractionalization. We have on an edge normally electrons that go to the right and they go to the left. What is done in the quantum Hall effect is that the quantum Hall liquid is splitting these into left movers and right movers that are separated in space. A similar thing happens in spin chains. So here we imagine ourselves antiferromagnetic spin chain where the spins are on average pointing a little bit in opposite directions. And they're typically described by a Heisenberg type Hamiltonian like this. What Haldane said in the early 80s, which was a big surprise to the community at that time, is that the integer and half-integer spin chains are qualitatively different. So the integer spins give gapped systems, and the half-integer ones are gapless. So one toy example due to Affleck and collaborators is if we look at spin 1 Heisenberg chains. What is happening is that in each of these blue blobs we have a spin 1 object. We want to think about these as being 2 spin 1 halves, and then at the end of the day projected onto the triplet states. So what are these effective spin 1 halves doing? Well, they're actually forming a singlet pair with their neighbors. And they are doing that throughout the chain, although on the edge you have nothing to pair up with. So you have excess spin 1 halves at the edge. And this is really fractionalization. Right? You start with a spin chain consisting of only spin 1s, and you end up with 3 spin 1 halves at the edge. Okay, that was it for the prize. Let me just say something very brief about the present and future. So last year there was a funny cartoon presented in Nature Physics, which listed the 10 biggest physics discoveries of the last 10 years. Only 9 of them turned out to be true, and actually 2 of them are blocked. That leaves 8, and 4 of them are on topological materials. If this would happen again in 10 years, if someone would draw such a cartoon, I'm pretty convinced that roughly half of them would again be topological materials, or at least that's my personal belief. So in the research today, we see more and more the aspects of symmetry and fractionalization coming into the theoretical work. And it's fueled by experiments. Haldane's toy model was the first of a big class of materials called topological insulators. And this has opened also the dream for future applications. That's what I had to say.
I'm passing microphone to Frank.
Can we turn this one on? Yeah. Okay, so I wanted to talk about something that's growing out of the Nobel Prize this year, but that wouldn't overlap too much with what other people are saying, and at the same time is very significant. So I chose to talk about the problem of confinement, which, as you'll see, was radically affected by the work of Kosterlitz and Thouless. So there's a lot to talk about, and at 1 minute each for these, I'll still be over time. Yeah. Okay, can't waste time. So first I will very, very quickly review, as already been discussed, the vortex deconfinement mechanism that Kosterlitz and Thouless invented, that was the central piece of what they got the Nobel Prize for. It had to do with a two-dimensional system of planar spins, the so-called XY model, SO2 symmetry of the spins, and a phase transition from a ferromagnetic to a not ferromagnetic-like state as a function of temperature. They showed that the key to their new kind of phase transition, this vortex liberation phase transition, was a battle between energy and entropy. The vortices formally have infinite energy. in an infinite system. In a finite system, their energy grows logarithmically with the size r. But their entropy also grows with the size because you can put the vortex anywhere. So there's the entropy being the logarithm of the number of possibilities goes like 2 log radius, or log radius squared. And therefore the free energy goes like kappa minus kT. There's a battle between energy and entropy, and the free energy for the vortices becomes less than 0 over a critical temperature. Then the vortices can rove free even though they had finite energy, infinite energy, and they get liberated. So we had objects that were confined. They're not in the low energy spectrum, but they do appear after a phase transition. That's a deconfinement transition. Ironically, vortex liberation is the flip side of spin wave confinement. In the ordered spin system, you can have small fluctuations, which would be, if you weren't in 2 dimensions, which would be massless spin 0 particles. It's subtle in 2 dimensions, but that's still morally correct. So speaking somewhat loosely, one has algebraic order, which is indicative of massless particles, and this is due to the unconfined Nambu-Goldstone spin waves. But in the deconfined vortex phase, the vortices disorder the spins, and then the correlations decay exponentially. In terms of the spin waves, that means that they've become massive, they've been removed from the low energy spectrum, their structure has been confined. So you trade confinement of vortices for confinement of spin waves. So that was a quick review of the essence of Kosterlitz-Thouless with a particular slant. Now let me talk about the phenomenon of quark confinement, which was a big mystery that Kosterlitz-Thouless shed considerable light on. Another question of confinement arises in the theory of the strong interaction. Historically, there was considerable circumstantial evidence for quarks in the late 60s and early 70s. These are objects out of which protons, neutrons, and other hadrons are built that have exotic quantum numbers, including fractional electric charge. But people looked very hard for these quarks, bashing things together with enormous energies and doing sensitive searches, and came up empty. Louis Alvarez even looked in moon rocks for quarks. For this reason, many sensible people were leery of taking quarks too literally as particles, including the sensible person Murray Gell-Mann, their inventor. So the situation became critical when we had an otherwise credible theory of the strong interaction, QCD, which had quite successful quantitative predictions, but one of its predictions is that things are made out of quarks with exactly those exotic quantum numbers. So now you couldn't avoid that problem. Right? The theory of the strong interactions was no longer a complete mystery. There was a candidate, and it had this problem of confinement. Now, but the problem also took a very specific shape. The quarks, which are not observed, carry color gauge charge in this gauge theory. So do color gluons, which are likewise not observed, whereas baryons and mesons, which are color singlets, are the things you observe. So the problem of quark confinement became the problem of confining color charge, this charge under this non-abelian gauge symmetry. Confinement of color charge and confinement of charge in general is actually quite natural. Indeed, since in a gauge theory it's only gauge invariant quantities that are physically meaningful, charge localized on a particle degree of freedom, which changes if you make local gauge transformations centered at that point, is kind of a paradoxical idea. Fundamentally, it is deconfinement that's hard to understand. That's an ahistorical example because we knew about electrons that are free charged particles for a long time, and people were prejudiced by that knowledge. But that ahistorical perspective, that it's confinement that's natural, deconfinement that's unnatural for charged particles, is realized in simple models like 1 + 1 dimensional quantum electrodynamics. You see the flux has nowhere to go, so there's a linear confining potential, a finite amount of energy per unit length. If you try to pull two electrons or quarks apart, or quark and antiquark, I should say. It's also formally jumps right out in the strong coupling limit. If you have a strong coupling gauge theory, you take the kinetic energy from Maxwell and the coupling to a current. If the coupling constant goes to infinity, that first term formally just vanishes, and then the equation of motion tells you the current is zero, which is to say, no charges anywhere. That's confinement. Okay, and each link of flux still costs energy, and so it's very much like the one-dimensional situation. The least energy is the shortest path, and that is a path that grows linearly with the distance, and you have a linear confining potential. In QCD, numerical work has shown that there's no phase transition as you go from strong to weak coupling. And asymptotic freedom tells you that the weak coupling in the discrete formulation gives us a rigorous construction of the continuum theory. So, since there's no transition, it's confining in strong coupling, it's also confining in weak coupling in the continuum limit. And sure enough, that's true. You can look at the numerical work, and in the numerical calculation, say, of what a baryon looks like, if you put down 3 quarks of different colors to make a singlet, you can calculate numerically where the flux tubes go, and it looks remarkably like that strong coupling expansion, except that the tubes are kind of fattened up a little bit. By the way, it doesn't look like this. Okay, so the strong coupling limit, by forcing the flux tubes to follow links, captures the self-stickiness of colored gluons, that gluons attract each other, which is also suggested by asymptotic freedom. The flux doesn't freely expand, but is focused. But we're close now to proving too much. We also want to accommodate QED, a gauge theory that does not confine charge. How does deconfinement work? Well, KT's work points the way, at least qualitatively. In the strong coupling expansion, one can connect different flux paths by putting down plaquettes of flux. That's a part of the Hamiltonian, so it's, if you do perturbation theory, you get all those terms. Each is accompanied by a 1 over g squared in the Lagrangian, as we saw, it's 1 over g squared f squared. And there's a battle between entropy from having more paths and this cost factor by having complicated paths. And you can map it onto the KT logic through this analogy, mathematical mapping. And here's a picture of many different paths. They get longer and longer and proliferate. Unfortunately, it's proved very difficult to make that argument precise. There's an open $1 million Clay Prize for doing that. It would be wonderful to have a weak coupling understanding of confinement in QCD based on liberation of appropriate disordered degrees of freedom, more closely analogous to the KT original work. Several candidates have been proposed for what those variables might be. Mirons, instantons, center vortices. Experts will know that none is one universal acceptance. But some beautiful, valuable insights have come from simplified models in special cases that really do build closely on the KT work. So let me very, very quickly walk you through 2 of them. 2 + 1 dimensional quantum electrodynamics was analyzed by Polyakov I should say it's augmented electrodynamics, where you also include the possibility of magnetic monopoles. This is what you would get, for instance, in a non-abelian gauge theory like SO3 in the Higgs phase. So you break it down to electrodynamics, but it also contains magnetic monopoles. The monopoles in that theory have an effect on photons that's mathematically very similar, almost isomorphic, to the effect of Kosterlitz-Thouless vortices on spin waves. So they disorder gauge flux correlations instead of spin correlations, rendering those short range. Another way of saying it is that the photons become massive. They are removed from the low energy spectrum. The low energy physics no longer has long range forces. It's a confined phase. A remarkable consequence of this is that the weak coupling theory, which is kind of manifestly a Higgs theory with particles getting masses from Higgs condensation, is continuous with the strong coupling manifestly confined phase where the gauge couplings take over, the Higgs field is a minor perturbation, and the particles are confined. Those sound very, very different, but there's no phase transition between them. Those are continuously related. Another remarkable example along the same lines is that BCS pairing is another dynamical way of getting a superconducting Higgs phase. And high density QCD, if you apply BCS methods, exhibits a remarkable form of pairing where the color symmetry is broken in a structured way called color flavor locking. This is what it looks like for aficionados. This is very analogous to the B phase of helium-3, where in that case it's not color indices, the Greek indices, and flavor indices, the Latin indices, which get paired together, but orbital spin and magnetic spin, nuclear spin. As a result, the original color symmetry is broken and the original flavor symmetry is broken, but a combination survives because the delta functions link color to flavor. And from that, you can read off many properties. The colored gluons acquire mass and become the observed vector bosons. That is, they have exactly the quantum numbers of things like the rho meson, the phi meson, and the omega meson. Similarly, quarks acquire a mass, the superconducting gap. There's a gap in the spectrum to producing things with quantum numbers of quarks, and they have the quantum numbers in this phase of the observed baryons. So the weak coupling BCS phase, which is all calculable, looks very much like what you expect in the strong coupling nuclear physics phase. And there's no barrier to continuity between them. In particular, confinement, following this logic, which came through Polyakov from Kosterlitz-Thouless, is a calculable phenomenon in weak coupling. So, quick conclusion. Kosterlitz and Thouless showed, by example, that confinement of one degree of freedom is often associated with deconfinement of a dual degree of freedom, and the seeds of all subsequent developments of duality is here. Well, for that matter, it's also in the earlier work on the Ising model by Kramers. But that they also showed that confinement could sometimes be analyzed as a weak coupling but non-perturbative phenomenon. I should say that confinement was very problematic in the early days of the strong interaction in QCD, and having that model was a phase transition in itself. It made what seemed like a desperate ad hoc assumption seem more plausible. It also made continuity between confined and Higgs phases and Closely related to this in condensed matter physics, superconducting and insulating phases credible, that no phase transition necessarily separates those very different seeming kinds of states of matter. That's an important conceptual unification, which is proving to be very fruitful too. More generally, Kosterlitz and Thouless was a strong early link forging the condensed matter field theory high energy connections that are so strong and growing today. Thank you.
I'm going to talk about the work of Haldane and also Kosterlitz-Thouless and discuss how they apply to quantum systems in 2 dimensions. A lot of this work was motivated by the discovery of the high-temperature superconductors in 1987. And I'll show some data from the latest data from the high-temperature superconductors and throw out some theoretical ideas of the possible connections to the topics of this Nobel Prize. So as Emil already mentioned, one of Haldane's important contributions was the semi-classical theory of quantum fluctuations in spin chains in 1 dimension. And what Haldane showed was that topological skyrmion textures had Baryes phases that turned out to have very important effects to their long-distance properties. And in particular, for integer spin chains, you obtain this AKLT state that Emil also showed, in which the spins form singlets between nearest neighbors, leaving spinor halves at the edges. So soon after this work, there was a lot of work trying to extend these ideas to 2 dimensions. So let me begin by mentioning what happens on the square lattice on mildly frustrated models of essentially the same Hamiltonian. So there, of course, the phase with long-range order, shown on the left, the Néel state, is stable, unlike in 1 dimension. But with sufficient amount of frustration, you can have then a phase transition to some sort of state that preserves spin rotation symmetry. And what Haldane also argued in an earlier paper, that here also there were topological effects associated now with instantons carrying Baryes phases that would lead to a sensitivity on 2s mod 4, not 2. So 2s mod 2 was the sensitivity in 1 dimension. And then we showed a bit later that, in fact, the way the sensitivity is realized in this model is by an actual broken symmetry, a lattice translational symmetry that appears as long as 2s mod 4 is not 0. A somewhat different phenomenon happens on the triangular lattice. So now again, let's take the same Hamiltonian, put it on the triangular lattice. Here again, as far as we know today, the spinor half system does have long-range order, but now in this more complicated non-collinear arrangements with the spins pointing to the 3 different directions on the clock. And now you can again ask, well, if they're semi-classical quantum fluctuations, are there interesting quantum effects, and what phase can you get without any broken symmetry? And indeed, it turns out in many theoretical models there is a phase, and one way to understand this phase without any broken symmetry here is actually by its close connection to the Kosterlitz-Thouless transition. Now, one of the things Kosterlitz-Thouless showed was the stability of a phase at low temperatures where the vortices were confined and the spin correlations have power law decay. Now, it turns out in two space dimensions for quantum systems, there's a similar phase here where a somewhat different type of vortex is also confined, but the spin correlations decay exponentially. Nevertheless, because of the confinement of vortices, there's liberation of fractionalized excitations that carry spinor half. And today we understand this at a much deeper level, and it's what's called a state with Z2 topological order. And in particular, it's been shown to be closely connected to Anderson's proposal way back in 1974 of the resonating valence bond state. So this is a state in which the spins form singlets, as shown in this picture, but then they resonate with each other so that the final wave function has a rather non-local structure. The more modern way of saying this is it has long-range entanglement and Z2 topological order. So now let me turn away from insulators, which is what the entire discussion was so far, but talk about metals. Is it possible to have exotic topological states in metals? And the answer is yes. Of course, however, the real impact of these ideas would be if they connect to some experiments, and I'll close with some speculations along those directions. So suppose I take an antiferromagnet of the type I've discussed so far, and say couple it to a bath of electrons that form a Fermi surface showed on top. Now, as I change the coupling between these systems, you can imagine two possible phases. In one phase, there's antiferromagnetic long-range order shown on the left, where phi is non-zero, and the other phase, phi is 0. So the phase on the right is a conventional phase with no broken symmetry, and since you have a finite density of fermions, they form a Fermi surface, and the volume enclosed by the Fermi surface is given by the Luttinger theorem. On the other hand, on the left, you have a broken symmetry, so the Fermi surface splits into what are called pockets, but nevertheless, this is a conventional broken symmetry phase, where also the modified Luttinger theorem is obeyed once you account for the broken symmetry. So I just want to raise the possibility here of a topological phase that can also appear in metallic states, and this does happen in various models, which I'll put in the middle. And very much like the Z2 topological order of the insulator of Anderson state, this can also be present in metals. And this topological phase now has some remarkable properties. You will see that it has no broken symmetry like the phase on the right. So it's like a Fermi liquid in the sense there's no broken symmetry. But like the phase on the left, it has small Fermi surfaces. And you can link the presence of these small Fermi surfaces to the presence of topological order. So we have a new type of metal in the middle in which the conventional Luttinger theorem has to be modified due to the presence of topological order. So one very curious thing about this phase is now detecting topological order becomes equivalent to detecting the size of the Fermi surface, which is, and that connection between the two builds on an argument of Oshikawa, and that allows us in principle to even measure topological order directly in experiments. So let me finish by just flashing possible connections to very recent experiments on the high temperature superconductors shown up on the upper right. And here's a very busy phase diagram as a function of electron density and temperature. For now, I just want you to focus on 3 different phases at higher temperatures, the AF, the PG, and the FL. And those, roughly speaking, I would like to identify with the 3 phases I showed you, AF, PG, and FL. The conventional phases are the AF and the FL, but is this topological metal a possible model for this PG? Now, there are numerous indications in experiments, which are very difficult to do, but lots of very clever techniques. People have indications of small Fermi surfaces, but absence of long-range order, certainly at high temperatures. And most recently, I think one very exciting advance has been the experiments of the group of Louis Taillefer, which are summarized here. These are Hall effect measurements. And as you go from small p to large p, what you see is, to say at large p, you have the conventional Fermi liquid phase. And then at small p, you have the antiferromagnet with the small pockets. And a huge amount of energy has been expended in understanding the green regime, where there's an additional broken symmetry. So, however, what's exciting about these observations is there seems to be a small regime here where there is no broken translational symmetry, and evidence anyway, so far, of small Fermi surfaces as measured in the Hall effect. So I think that's one of the open questions. We're trying to understand this phase diagram, and in particular why TC is so high. But we are making progress, possibly through these models with topological order on those questions. So I'll end there.
Okay, so I should thank the organizers of this panel, as well as the previous speakers for covering a lot of the introductory material. And what I'll try to do is to focus on some of the recent, developments that come out of work that was done for this prize. And if I have time, I'll try to talk about 2 topics, topological phases, at least in their new incarnations, and the topic of duality. And taken together, they sort of cover the 2 aspects that were mentioned in the citation, topological phase transitions, which relate to duality and topological phases of matter. Okay, so just to set the stage, we saw this beautiful formula that Duncan Haldane spent some time talking about, how to calculate the topological index of a Chern insulator. It's related to the integer quantum Hall effect. So the Chern number that you obtain after this, when you calculate this integral, is related to physical properties like the Hall effect, of course, the quantized Hall effect, or another more direct way of visualizing that is the existence of edge states. Okay, and so we'd like to think about how to generalize this physics. The fact that you have an insulator in the bulk, something that is essentially trivial if you simply looked at it in the bulk, but if you get to the edge, you see that there's something interesting going on because of these gapless metallic edge states. Okay, so one simple way in which you can generalize this is think of a three-dimensional band structure. So now you have a three-dimensional Brillouin zone, and you can look at sections of the three-dimensional Brillouin zone, okay, which are two-dimensional band structures. Apply the beautiful formula that we saw in the previous slide and calculate the Chern number. And this Chern number can actually vary as you proceed through the Brillouin zone. It could be 1 in the blue shaded region in the middle and 0 in the outside. Okay, and it turns out that this defines an interesting state of matter called the Weil semi-metal. And a direct consequence of the fact that you have edge states in the two-dimensional case is that you again have some interesting surface states. In this case, it turns out to be a part of a Fermi surface, an arc. Two-dimensional Fermi surfaces have to be closed, but it turns out in this particular case you can have half of that two-dimensional Fermi surface. The other half is on the opposite, the bottom surface of this material, and that's one generalization that's been interesting recently. Another one, which was mentioned again in Duncan's talk, is you restore time reversal symmetry, and you look at the interplay between symmetry and topology, okay, and that leads to topological insulators. And one of the interesting aspects here is that you can also realize them in 3 dimensions. So in 3 dimensions, again, you have an insulating bulk, but if you look at the surface, it turns out to be metallic. Okay, so and in fact, it's a very unusual kind of metal, which is described by a single Dirac cone that wraps around this insulating bulk. Okay, so there's an interesting interplay between symmetry and topology. That's the second way in which these have been generalized. And the third way, which has been very exciting for a lot of theorists, is to generalize the notion of these topological phases. The previous examples I gave can be thought of as free fermion topological phases, non-interacting particles. What about systems where the interactions between particles are very strong? And we already know of one interesting example. The one-dimensional chain that Haldane showed was a gapped phase, and subsequent work showed was actually a very interesting kind of gapped phase. Although it's gapped in the bulk, if you retain spin rotation symmetry, you get gapless excitations, spin-a-half excitations at the edge. It's an example of an interacting topological phase. This occurs in one dimension, but more recently we have realized that these kind of interaction-enabled phases can occur in higher dimensions as well. Okay, so previously, at least when we started thinking about this physics, the usual logic was there's integer quantum Hall effect, that's a property of free fermions. You add strong interactions, you get the fractional quantum Hall effect. Okay, but it turns out that there is some space in between. There's physics of interacting systems. You get new physics because of interactions, but it's not the fractional quantum Hall effect. In fact, it's more like the integer quantum Hall effect in the sense that the physics of, for example, there's a bosonic analog of the integer quantum Hall state. In the bulk of the system, there's nothing very exciting going on. There are no anyons or novel excitations. You just have the regular bosons. But if you go to the edge, you find that there are edge states. And this physics only arises in a system of interacting bosons. Okay, and one of the interesting things that occurs over here, you can calculate the Hall conductance of this system. And you might expect it's an integer in the usual quantization in terms of the charge and Planck's constant. But it turns out it's only allowed to be an even integer. Okay, so when you have bosons, and you make these demands that you have a trivial bulk, you can get a Hall effect. You can get a Hall conductance, but it's always 2 times an integer. Okay, so that's one the kind of results that we have recently been able to extend the original physics of free fermions to these new kinds of states. So that's one direction, finding new interacting phases of matter that have topological properties. Okay, another direction in this area of adding interactions to topological phases has been to stick with topological phases we identified before, but look at new phenomena that occur because of interactions. Okay, so I just mentioned there are these 3-dimensional topological insulators that can have Dirac cone metallic surface states. Well, it turns out that's one phase of the surface. If you allow for interactions between electrons on the surface, you can get other phases. So people have described other phases like, for example, a superconductor on the surface, or something that is magnetized on the surface that leads to a gap to these Dirac fermions. But both of those examples break the protecting symmetry. Okay, so you can ask, can I retain all of those symmetries but still get an insulating surface state? Okay, now the naive answer to this question is no, but it turns out that if you're willing to pay a price, the price being that you allow for fractional excitations, like in the quantum Hall effect, if you allow for those kind of excitations at the surface, then indeed you can gap out the metallic surface, and you can trade it, if you like, for a state that's analogous to a fractional quantum Hall state. In fact, it's very analogous to the state that's believed to be seen at the filling factor of 5/2. There's a slight difference. It's a distinct state. We call it the T-Pfaffian, and this is allowed to exist on the surface of a 3-dimensional topological insulator. It's consistent with the bulk, and it could, it's one possible surface termination. Okay, so for a long time, I would say these words, and people would ask me, how do you get this surface state? And I really didn't have a simple picture. But over the last year or so, we have come up with a simple way to understand this physics, and that really rests on the idea of duality. Okay, so let me briefly, I won't really be able to explain the details, but in a simple way to describe physics of many systems, as Frank mentioned, starting with the 2-dimensional Ising model, or if you had a film of superfluid helium, you could either describe it in terms of particles that form a Bose condensate, or in some cases you may prefer to describe it in terms of some collective excitations, topological objects, which are basically vortices. Okay, so these two descriptions, you have a choice. You can use one or the other, and in some cases it pays to use the second description. Okay, describe the system in terms of vortices, and things simplify. One example where that occurred was in the description of the phase transition by Kosteles-Thouless, where you think about the phase transition between the low and high temperature phase of a 2-dimensional XY model, not in terms of what all the spins are doing, but in terms of what the vortices are doing. Okay, so you can take a problem that's hard in terms of one set of variables and simplify it by looking at the dual set of variables. Okay, and of course, the interesting question is, this is a classical system. What are the quantum generalizations of this? And we heard a little bit about that in Haldane's talk about the spinor half chain as being viewed in a similar light. But really, the most quantum mechanical objects that we have are fermions. Okay, so is there a dual description of fermions? And recently we have, one of the simplest settings is to ask what is the dual description of a Dirac fermion in 2 dimensions. Okay, so let's say you have electrons with a Dirac dispersion, as you get on the surface of a topological insulator. Is there a way to describe this in terms of vortices? Okay, and in fact there is. This relates to earlier work done in the context of quantum Hall effect, but this is a sort of a relativistic generalization of that. Okay, and it turns out that the vortex theory of Dirac fermions turns out to also be excitations, fermionic excitations, which have a Dirac dispersion, composite fermions. But here they are coupled to an electromagnetic field. So very much like vortices interacting through spin waves, these are fermions that interact via a photon excitation. Okay, so that's the complicated way of saying the same thing. But now you can try to utilize this duality, do something simple in terms of your new variables, and that turns out to be something very complex in terms of the original particles. Okay, so what's the simplest thing we could do over here? One thing you could do is just to look at superconductivity of these composite fermions. Okay, and it turns out that that is exactly this T-Pfaffian surface state that I mentioned before. It preserves all of the original symmetries of the problem. Okay, there's another application that I can briefly mention where you can utilize this duality to shed light on an old problem. The problem being what happens when you have a Landau level exactly at half filling. Okay, so that's a system that has a certain symmetry. You can think of that as being either half full or half empty, and it turns out that this duality allows you to keep track of that symmetry. Okay, so you apply a magnetic field on Dirac fermions, you get Landau levels that are automatically half filled. They retain this particle-hole symmetry. That's the left-hand side. And you can track through this duality in the new variables and ask what happens. Okay, and hopefully that's something simple that happens. And in fact, what happens is simply filling up these Dirac fermions, these composite fermions, up to some density. Okay, these composite fermions are really vortices. You apply a magnetic field, you get a finite density of them. Okay, so the prediction is that this half-filled Landau level realizes a metallic phase that was known before in various theories. The new input that you get is this metallic phase looks like a Dirac fermion that's up at some finite density. So these are Dirac composite fermions. Okay, and there's some numerical evidence that this is indeed the case, what's happening in the half-filled Landau level. Okay, so let me conclude. My main message is that we had all of this beautiful physics we heard about, which seemed distinct, right? The Chern insulators on the one hand, topological defects, costless Thouless on the other. Recent work has shown that there's a deep connection between these different appearances of topology, these apparently distinct appearances of topology in condensed matter, and we are having a lot of fun trying to establish these different connections.
I've done this once before, and it makes me feel like a telephone operator from the old days. For those of you who are above a certain age, you'll remember that. Okay, so since there were many of us, and at 5 minutes apiece, I knew we would be done in no time. I decided to go last and to try and orthogonalize on the fly, since by now you should really know everything. Okay, so I'm going to use a piece of chalk the moment it becomes available. The very tiny piece of chalk, so I'll start with that. It's a fractionalized piece of chalk. Okay, and another tiny piece of chalk. That's two now. I think you might ask the Nobel Foundation to fund you for thank you. All right, good. So I have three things to say. The first of these is just going to add to what everybody said. I just want to draw for you a chart of some intellectual connections. Obviously, like everyone, these are things that I know about, so I'll put arrows between them, and then maybe members of the panel will correct me when I'm done. So there are sort of many aspects of physics which have the term topology applied to them, and so let me try and write down a few of those. So there's the Aharonov-Bohm effect, which is topological in the sense that you go around something and it doesn't matter at what distance you go or what the precise details of the orbit are as long as you go around. There's the Berry phase, which is again topological, and of course for those of you who know your theory of a single spin, okay, this can be that. It's the Aharonov-Bohm phase of a monopole for certain problems in some sense, but more generally it's a statement about connections in Hilbert space, and this began as a statement about connections for vector fields in real space. All of this of course, has to do with gauge theories, of which electrodynamics was the first one to be discovered long before. Then there are sort of
TQFTs, topological quantum field theories, some of which look like gauge theories, maybe all of them look like gauge theories. There is the topic of defects, solitons, instantons, on which Igor is an expert, so you should ask him afterwards. This connects to one of the prizes, one of the topics for the prize, which is defect-mediated phase transitions. The work of Kosterlitz and Thalus. The Berry phase connects to band topology, although then we have the topic that Ashwin was just talking about. I really apologize for my handwriting. Interacting topological phases of condensed matter systems. And so, as he noted, in here are generalizations of the ideas developed in band topology. On the quantum Hall side of it, there's the connection to gauge theories and topological quantum field theories, Chern-Simons theories. This connection also exists, and this has also been referred to, and this goes via the idea of fractionalization. Right? So already so let me go a bit further and write down here integrable systems. Let me just write the universe of 1 plus 1D systems. So these are integrable CFTs, bosonization, and all of those end up having intimate connections with the theory of solitons and defects and instantons in one dimension. That was most of what I wanted to put down. So for instance, in the simplest examples of fractionalization are right in 1 plus 1 dimensions, where you have some obvious solitons, polyacetylene. And certainly in the intellectual trajectory of condensed matter physics, it was very important that this connection existed in order that the fractionalization of higher dimensions, as in the fractional quantum Hall effect, got discovered. For instance, Laughlin's first paper on the topic, which was wrong, was actually trying to generalize basically a more literal version of what was going on in 1 plus 1, and then he got the right idea. So the thing I want to say, I guess, in putting this up, is to say that, if you ask yourself where we might be going from the discoveries that this prize is about, sort of in the future, it's kind of useful to look back a little and see that all sorts of things end up being connected in ways that you wouldn't have known. So that's both encouraging in the sense that there are connections to be discovered, such as the ones that Ashwin was just talking about, and also perhaps suggest that it can be a little hard to predict which particular connection will come by. One thing I'll put on this, and then you can ask Subir about this in the question time, is there's of course this important idea of holography, which is floating around, and exactly where to put this on this collection of ideas I'm not completely sure, so I'm going to say something speculative and no doubt therefore wrong, which is that so holography has to do with, sort of a duality between theories that involve gravity and then what to us look like ordinary field theories, which for certainly those of us who are condensed matter physicists are the ones we care about most deeply. A lot of the work involves dealing with a static gravitational bulk. On the other hand, the full connection involves a gravitational field which is fluctuating. And to my untrained eye, a fluctuating metric starts to look somewhat topological in the sense that it isn't a fixed geometry. And so whether in some fashion holography is an interpolating idea between things which are very topological and things which are not very topological, I think is maybe a speculative thing I might say at the broadest level going forward from a picture like this. The second thing I have to say is extremely narrow. So we mentioned many connections. I'll mention a very small one. So the Haldane phase, after Duncan's initial work, was realized in this AKLT model. Also, one of my colleagues, Elliot Lieb, played a central role in that. the wave function for the ground state wave function for the AKLT model is particularly simple. And then in later work, I think by Stellan Oslund, the connection was made between that and what we now call matrix product states. And so that actually was a very useful case where there was a ground state of an extremely interesting model, which turned out to be of the class of this new set of wave functions. And the MPS idea, of course, has turned out to be spectacularly useful. It's a way of thinking about wave functions, more broadly tensor networks, which has completely changed the way condensed matter physicists do wave functions. When I was a child, wave functions were things that people wrote down by inspiration. Laughlin came along and wrote down a wave function, or somebody else, and and there was no systematic understanding of when wave functions were good, variational wave functions for many-body systems, and when they were not. And this business of the ideas of entanglement, matrix product states, tensor network states has completely changed, and it made very systematic how we think about it. So even this small corner of this research that we discussed today actually has a connection to a much larger one. The last thing I want to say is just on this general topic of topological orders in condensed matter systems. So one thing to note is that unlike broken symmetry, topological order, of course, is a weaker form of order. There's, as it were, which is what allows the universe of possibilities to expand. With broken symmetries, there's a very strong set of ideas. You have an order parameter, you have something like a sigma model, there are defects, there's even a hydrodynamics, and so there are all sorts of things that just come in a single package once you've identified a particular broken symmetry. For topological orders, things are more complicated. The long wavelength field theory is topological. And so in a sense, you have to back away from that limit in some fashion in order to see things which you can then look at in experiments. So the upshot of that is to say that I think learning how to measure and do experiments with this new universe of orders, we've come a long ways, but it's certainly a case where I think lots of new ideas could be useful. The most spectacular example is the quantum Hall effect, but that happens to be a very special one where the Hall conductance, which doesn't have to be there, can be measured very precisely, and therefore allows experiments to be done to great precision. So in terms of topological order, I would say, their dynamics is a subject which is quite a bit open. Of late, there's been some work on their non-equilibrium dynamics, part of a general efflorescence of work on non-equilibrium quantum dynamics. And then the other, maybe somewhat speculative thought I want to leave you with is that when you build condensed matter systems which exhibit topological order, they of course, they're not actual donuts of stretchable size, right? They're actual systems. In other words, they come with a geometry. So what you generally do is you start with a system and you manufacture degrees of freedom. Maybe loops, for example, is the simplest case, which can be of any size. There's sort of a string tension which is close to zero. And so you're able to sense the topology of some underlying state because you have these degrees of freedom which can which are very different. They're sort of loop-like, string net-like degrees of freedom. So in a sense, this is also backing away from the topological limit, but it would be interesting if one could detect these degrees of freedom in some more systematic way. One example where it does work is the system of spin ice, where a gauge variable turns out to be the spin, and so that you can detect by sort of standard neutron scattering methods. But in more complicated systems, such as the one Subir was describing, the gauge field and its are sort of multi-spin operators, and perhaps there are string operators of some sort which are needed. So that's an area where I think going forward we would make progress by having cleverer ideas on how to look for these things. So I think I'll stop with that.
Now I would like to invite brief remarks from panel members on what was said, if there are any. After that, we will move to audience questions.
One small remark is, I think another entry that belongs sort of in the prehistory or top of this diagram should be Dirac's work on magnetic monopoles, where that was very topological, had the ideas of gauge field topology, and in particular, the invisibility of the Dirac string, which was key to his quantization condition, is implicitly also has the Aharonov-Bohm effect, because the Aharonov-Bohm effect is precisely the fact that if the quantization condition is not satisfied, the string is visible. So I think Dirac knew about that. And yeah, so I don't think people fully appreciated the power of Dirac's work, but it really was very seminal. Yeah.
I think also another example of early work is London's work on flux quantization. Was way ahead of its time. Any more remarks?
I can make respond to Shivaji's comment on holography. So holography does indeed map a theory of quantum gravity to theory on the boundary, but quantum gravity, at least most theories of quantum gravity, are not purely topological. They have gravitons and other real excitations, which gravitons in particular map to energy fluctuations and thermal effects on the boundary. So I don't see a connection.
Maybe I can sharpen.
Yes.
The question is, can it be an interpolation somehow? Because as the amount of fluctuations can interpolate the limits. That was the question.
It's possible. I mean, there's certainly, holography describes in the simplest context conformal field theories, and it's possible to deform conformal field theories so they become purely topological, but involves opening a gap or something. Yeah.
Any further remarks?
Well, I think we should give the audience a chance.
Now I invite questions from our audience.
I have two questions. One of them is actually not as much a question as a comment that many, many years ago, I mean, when John Bell was still alive, he died in 1990, he had seen a paper by Roman Jakiv in which he also had fractional charge creeping up the walls. Is that related to this thing? That's what the first question.
Yeah.
It's absolutely that. Okay.
Yeah, there's a paper of Jakiv and Rebbe, which is its literal content is 1 + 1 dimensional domain walls, but there they identified a zero mode. If you realize that the surface of a solid is like it can be like a domain wall. Okay, you have an effective mass inside and a very large effective mass outside, but those masses might be the same sign or the opposite sign. If they're the opposite sign, it's a domain wall, and you have zero modes. And I think a lot of the theory of topological insulators is just spelling that out.
Okay.
Yeah.
And the second question is that, is there any relation between the anomalies in quantum field theories and theta parameter of QCD with the things we're talking about today?
Yes. But it gets very technical very fast. But I could certainly, I don't know if anyone else wants to take that up. but yes, there are tremendous connections. In fact, again, going to the topological insulators, the topological insulators can be thought of as materials in which you have a theta parameter equal to pi, or an odd multiple of pi, on the inside, and 0 on the outside, or a normal material or vacuum on the outside. And that has to do with this change of sign again, because to change the sign of an effective mass, you make a rotation, a chiral rotation, which, because of the anomaly equation, changes theta by pi. So you can trade the negative mass for theta equals pi.
Actually, I shouldn't have commented on anomalies.
Yeah. Maybe one comment I could add to that is the idea of anomalies is very useful for characterizing the edge states that I talked about. So the way I presented it was these are states that are possible at the edge of an interesting two-dimensional system, but not on their own, not if they were realized on their own in that same dimension. And one way in quantum field theory to characterize this is to say that they are anomalous theories. And anomalous in the sense there's something about them, they look okay, but there's something about them that's actually problematic when you switch on the quantum mechanics. Yeah. Yeah, so the specific anomaly here, I think they're called Toft anomalies. If you think about implementing a certain symmetry while you have this particular dynamics or this particular theory, then there's some conflict. And the way the conflict is resolved is they are not, individual systems, they're actually attached to an interesting bulk phase. Yeah. And for example, what I talked about, this new type of surface state that we predicted for the topological insulators, one way to say it is it has the exact same anomaly content as a single Dirac cone. And that makes it a candidate for the surface. So the idea of anomalies has been very kind of useful in trying to, you can sort of port over a lot of technology that was developed there and cast this problem in that language.
Another aspect of it that's maybe simple enough to mention is that in the quantum Hall effect, you can describe many of the states, probably all of them, using gauge theories that have an anomaly in the bulk that gets canceled when you include the surface theory. So the theory as a whole has to be gauge invariant, has to have no anomalies. But the effective theory that governs the bulk does have an anomaly. It gets canceled by surface.
Yeah, there's another feature of anomalies I think that's also perhaps useful. So, for example, in Haldane's work, the long distance property of the spin chain depends sensitively on whether the microscopic spin is 1/2 or 1. From the point of view of traditional field theory, that seems very surprising. And how could some UV property, very short distance property, so precisely control what happens at long distances? But if you cast it in the language of anomaly matching, that starts to make sense, that there's some short distance anomaly that controls the long distance properties. Yeah.
More questions? You can either speak loud, or I can bring microphone.
You can ask for the role of topology in theoretical physics. Is it useful to pursue when topology entered at all the thinking in theoretical physics? Gauss was praised by the he would not have touched it. A very clear statement. So, is it a useful question to ask that topology, fascinating as it is and endless as it is, has entered at a stage where theoretical physics had many things to unify, and topology is definitely out of it, of the old physics, and comes to us as a surprise in ever new experiments in the Costa-Rica thing as well as they themselves express. So is it anthropologically a useful question to look for the origin of this multiplicity of topological cases we now discuss in the experiment very usefully, but that
I think, yeah.
You have left geometrization. This is the question for Frank.
I'm not sure I understand exactly the question, but let me answer a related question, which is what are some early uses of topology in physics that way predate the things we're talking about today? And I'm somewhat of a student of the works of James Clerk Maxwell. And in Maxwell's works, you find quite a lot of the discussion of linked circuits and the phenomena that happen. And he refers to Gauss and linking number and has an interpretation of it in terms of magnetic monopoles. And he also, in another paper called On Hills and Dales, developed a theory that later is the essence of what later became Morse theory, studying, which is a very important branch of topology. So, you can find a lot of stuff in Maxwell, and I highly recommend it. The other thing I could mention is that was very remarkable in the 19th century, and was in some ways the historical origin of work on solitons and topology, was the vortex theory of atoms by originally Lord Kelvin. His observation was that atoms are stable objects, right, and how do you get stable objects? This was, of course, before quantum mechanics was known. What keeps them? And his idea was that atoms are knots in the vortex, in the ether. And this inspired his friend Tate to make a very elaborate theory of knots, which was pioneering in mathematics and has had enormous influence. So, and it turns out that Skyrm, of the Skyrm model, was directly trying to implement Kelvin's crazy idea of vortex atoms as an alternative way of understanding nucleons.
And maybe my recollection is wrong, but isn't it so that in that paper, Kelvin made some kind of remarks that now physics research is over on fundamental questions are answered?
No.
No?
That's a legend, that's not. No.
Or something.
That's a misquote of Maxwell, where he said almost the direct opposite. He said that sometimes it appears that physics is down to just measuring things more and more accurately, but that's preparation for finding discrepancies and making big discoveries. So it was at the dedication of the Cavendish lab. He wanted to encourage experimentalists to do things accurately and not get bored with it.
Maxwell died in 1879. But Kelvin was alive.
Yeah, they were good friends though, and corresponded quite a bit, as did Tate. There's a whole body of correspondence. Very.
Also, interesting aspect is that both Skyrmi model and Kosterlitz-Taulis came out of the same university, Birmingham. So, and similar thing, experiments on Wurzen helium were performed there.
Tony Leggett was an undergraduate student with Skyrmi.
He thanked in the paper for his help with calculations.
So it's. More questions? More questions? So maybe I would ask another historic question. So these are maybe some people on the panel or in the audience can answer this historical question, because it's interesting how these ideas were developing, and many. Talking about Kosterlitz-Taulis, for example, many great minds were thinking about this direction to advancing to various degrees. And for example, I think the closest is work. I will list few works, and I'm interested in the question how much of these works were known at around the same time, did they influence directly, or were they forgotten? And one of the work is work by Berezinski, and I don't know how it was done in Moscow. I don't know how well it was known in the West. And another, I think also Richard Feynman was also thinking about Kosterlitz-Taulis. I don't think he published anything, but once in a while in the papers for that period, there appear some statements asking, thanking Feynman for something. And of course also there was Onsager, who was thinking about conventional phase transitions in terms of proliferation of topological defects. Conventional, I wonder, was it like, had it any impact, or was it forgotten and then rediscovered later? Frank, do you know?
Well, that was basically before my time. I do, well, as I alluded to though, it was very, so I think Kosterlitz-Taulis was 73 or 74?
73, 73.
Yeah. So that was about the time that QCD was just taking off, so to speak. It was becoming clear what it was exactly and that it was credible. But confinement became a very critical problem. And I was just a beginner, so I was very ignorant. I certainly didn't know about Berezinski, but the Kosterlitz-Taulis paper was so clear that even I could understand it at that time. And it was very reassuring to see that you could have confinement and talk sensibly about these things. and that was, and then the Polyakov paper was not much later. So it definitely made the very bold step of going ahead with this theory, even though it had particles that don't exist. It made that psychologically easier.
Interestingly,
memory is a little hazy, but I think if you look in the second of the Clayton papers, I think by then Dzerzhinsky's work had already been brought to their attention. So they didn't know it when they did it, but they knew it, I think, very, very soon. That's one. Second, actually, going back to something Frank said, that what was the problem of confinement when he was young? That from the, again, in condensed matter physics, looking for deconfined phases turns out to be much harder. Confined phases we've known all along. And so, in that sense, it was interesting to hear him say that there's certainly that's, as Subir was pointing out with magnets, getting something which, a columnar pattern or something that is under confinement, that sort of stuff.
So in a way, electrodynamics is very misleading because it makes you think that deconfinement is easy and natural, but in fact, deconfinement in many ways is what's hard to understand.
Igor, maybe you can comment about what the content of Dzerzhinsky's paper vis-a-vis what we know about costless dollars is.
There were two papers, and in between there was a PhD thesis. And in the first paper, I think he misunderstood the origin of low temperature phase. He called it a phase with infinite susceptibility. So it was he was just a PhD student, and there was dominance of the notion that superfluidity is described by order parameter, and then it took him the idea that you have superfluidity without a order parameter. It actually came in his PhD thesis, and also he realized that there is a phase transition between superfluid and normal state driven by proliferation of vortex-antivortex pairs, and he made the mapping onto Coulomb gas and say that there will be this vortex-antivortex proliferation transition. That also comes in his second paper, which was published shortly before costly starts. But he did not have correct theory of the phase transition. And if you look at his PhD thesis, he actually tries hard. He actually has a Villain model in his PhD thesis, and he tries hard to find order parameter there. And so he didn't have a jump in superfluid density. So there's.
He didn't have the RG equations.
Yeah, this was also only appeared in later developments. So, but here certainly he understood role of topological excitations, but didn't have correct theory of the phase transition. And also another interesting aspect, Frank mentioned readability, and typically in the East, if you have two readable papers, it was not necessarily appreciated in the journals. You must have, there was appreciation for technical details, but it's a very rare case that Berezinski paper were rejected from JET journals without review, and the rejection was that it was too technical. This is what I heard. This is what I heard from people in Moscow. I don't know if it is true or not, but it was rejected.
Instead of saying it can be shown that, he actually gave details.
Yeah, he was then, and apparently. So I think it appeared later. It was accepted after it was rewarded. So interesting. I think Polyakov, he was opponent on his PhD defense. So there was a lot of interconnection of these developments. So I'd like to pass.
I mean, it's clear that Lars Unsager's paper was extremely important. I mean, apparently his thesis was rejected in Trondheim. They did not understand it, and he couldn't get a PhD on that. But that's what they say. I mean, I haven't checked, okay? But on the other hand, I mean, all the speakers this morning, both of them, they referred to it. And many of our great physicists like Yang and others, they really have all worked on that thing. Yeah. So it was very fashionable, and it was very, very influential. It's just that the younger generation, we never got exposed to it. I'm not young, but I'm compared to them, I'm younger. But honestly, we didn't get really exposed to these things. So they were all thinking about this solid state stuff. And but yeah, that's what I.
So, more questions? So, yeah, I think we are. So there are no more questions. I think we are now ending right in time as we planned. So let's thank speakers again.